Hello guys, how are you? I hope all of you are doing great. And some of you have asking me for a while that for some videos on thermodynamics, and so I have come with this video, this wonderful lecture about thermodynamics. And so let's enjoy this video, and don't forget to subscribe and share with all of your friends so that everyone get benefit from this all the lectures which is going on. Okay, and so let's start and enjoy this journey. Okay, first of all, we are going to discuss about the thermodynamics in general. What does it mean? Thermodynamics means what? Okay, thermodynamics is a macroscopic approach. Okay, we study about the macroscopic properties of pressure, temperature, and the volume of a system. In this study, the approach is macroscopic, but in statistical physics or statistical mechanics, the approach is the microscopic one, right? So thermodynamics deals with internal macroscopic state of a system. Okay, and internal energy, some of the functions involved in thermodynamics are really important. One of these is the internal energy. Internal energy is the sum of all types of energies constituents of the system, like translational energy, vibrational and rotational energies. These are all the constituents of those systems. Okay, then heat is a form of energy, right? It is a form of energy. So how heat flows due to temperature difference. If there is a temperature difference, like there is a high temperature in one region and another region is the temperature is low, then temperature will flow in that region, like, right? So these are the two properties of heat. So types of systems in thermodynamics, there are three types of systems in thermodynamics: open system, closed system, and isolated system. Open system is that system in which we can exchange energy as well as matter. Okay, can exchange energy as well as matter with its surroundings. Open systems can exchange those matter and energy with its surroundings, and closed system can exchange energy, right? It can exchange heat in the form of energy, so it can exchange energy but not matter. Okay, it can't exchange matter. An isolated system can't exchange both of them. It can't exchange energy as well as matter. Okay, and one really important concept of thermodynamics is the equilibrium, thermodynamic equilibrium. Whenever there is an equilibrium, heat will not flow. Okay, properties of the system that are independent of time. In equilibrium, in thermodynamic equilibrium, with time, everything will be constant. It will not change. System will not change with time in thermodynamic equilibrium. Okay, and equation of state. In thermodynamics, equation of state is really fundamental and really important. This represents the relation between pressure, volume, and temperature. So equation of state, this is the PV equal to nRT, right? PV equal to nRT. This is the equation of state. State functions. Which are the state functions? Depends on initial and final state only. If a thermodynamic functions depends on only initial and final state, that will be state function. Okay, and if it depends on a path what it follows from initial to final position, okay, then it is called path function. Okay, and there are variables in thermodynamics. Some of the variables are intensive and extensive variables. Okay, intensive variables are independent of division of system. if we divide the system, this properties, this intensive properties will don't change, which will not change if we divide the system, like pressure, temperature and density will not change if we divide the system, and extensive variables will change if we divide the system. If system will get divided in different parts, variables will change. Number of particles, these variables are extensive variables are number of particles, volume and internal energy. Okay, so work done in cyclic process. In cyclic process, area enclosed by the cycle in a PV curve, this is the PV curve, right? In PV curve, area enclosed by the cycle will be the work done. This is the cyclic process, right? Okay, that is change in work, that means total work done is area of rectangle ABEF. This is the whole rectangle minus what? Minus area of CDEF. Area of CDEF. We will get that work done in this cycle. Okay, work done is positive if cycle is traced clockwise. Always remember that if cycle is traced clockwise, work done will be positive. If cycle is traced anti-clockwise, the work done will be negative. Okay, this is very interesting, and this is very, remember that. Okay, and gas laws for ideal gas. Okay, for ideal gas there are some laws. This is the Boyle's law. At constant temperature, P proportional to 1 by V. Okay, Sar's law, according to Sar's law, at constant pressure, P proportional to T, right? And according to Avogadro's law, at the same temperature and pressure, at the same pressure will be same and temperature will be same, then equal number of molecules will be present in equal volume of all gases. Equal number of molecules will present equal volume of that gas. Okay, remember that. And so we can write N1 is equal to N2, right? And fourth is the Graham's law of diffusion. This is the law of diffusion. Okay, R1 by R2 is equal to root over density of 2 by density of 1 when two gases are at the same pressure and temperature. Okay, at the same pressure and temperature, when two gases are allowed to diffuse into each other, the rate of diffusion, this small r is the rate of diffusion of each gas, is inversely proportional to the square of root of density. Okay, the rate of diffusion will be inversely proportional to square root of density, okay, of that gas. Okay, that is really interesting. Then move on to the fifth law. This is the ideal gas equation. We have studied earlier, equation of state, PV equal to nRT. R is the gas constant, which have the value 8.31 joule per mole per Kelvin, right? And sixth, the average kinetic energy. This is not a law, but this is the average kinetic energy we can calculate from equation of state in different thermodynamic processes. Okay, average kinetic energy is it is the average kinetic in 3 dimension, 3 by 2 kVt, and in 2 dimension it will be kVt. Okay, and in 1 dimension half of kVt. Okay, and average velocity, this comes most of the exams. Okay, remember and understand this concept. Average velocity or average speed is equal to root over kVt by pi m. We can calculate from density or the equation of state of the process. Okay, root mean square velocity is root mean and square velocity of that particle is root over 3 kVt by m, and most probable velocity is equal to root over twice kVt by m. These are really important formulas, remember this. Okay, and Van der Waals equation of state. Van der Waals gave some corrections into the equation of state, right? Van der Waals equation is that P plus A by V square. This is the Van der Waals equation of state. P plus A by V square into P minus B equal to RT for 1 mole of gas. When there is n mole of gas, this will be the formula, P plus n square A by V square, okay, into V minus NB equal to nRT for n mole of gas. And heat capacity for solid and liquid and for gas will be different. For solid and liquid, this is the definition and the relation and the formula. The amount of heat required to change the temperature of sample by 1 degree or 1 Kelvin will be the heat capacity of the solid or liquid. We can define heat capacity like this: C equal to dq by dt, the unit is joule per Kelvin, okay. And 1 Kelvin is what? 1 Kelvin is 4.186 joule. You can remember this. 1 Kelvin is equal to 4.186 joule, okay. In solid, Cp minus Cv is equal to 0. We know is gas Cp minus Cv is equal to nRT, but in solid Cp minus Cv will be 0. This is different. And specific heat of solid and liquid will be amount of heat required to increase the temperature of 1 gram of that sample of liquid or solid by 1 degree centigrade or 1 Kelvin. This is the dq is equal to C delta T, or we can famously say M delta T or MC cat, right? This is interesting, okay. dq is equal to MC cat, and Q is equal to M LF is the latent heat of fusion. Q1, we can write the formulas of Q in the case of latent heat of fusion and vaporization in the transitions, okay, like this. See the specific heat capacity. And molar heat capacity. Molar heat capacity is for gases, okay. For gases, heat required to increase the temperature of 1 mole. Heat required to increase the temperature of 1 mole of gas by 1 degree centigrade or 1 Kelvin is the molar heat capacity of that gas. There comes the concept of Cp and Cv. Cp is the specific heat at constant pressure. This is the dq by dt at constant V. Cv is the dq by dt at constant V, okay. And the relation is that Cp minus Cv is equal to Nr, okay. Cp minus Cv is Nr, okay. This is the relation. And one important and most of the times comes in exams, the value of gamma. Value of gamma is Cp by Cv. We also can write like this: 1 plus 2 by F, okay. Really important. And molar heat capacity, okay. Molar heat capacity is Cp minus Cv is equal to R. Atomic heat capacity is Cp minus Cv is equal to Kb. Also remember the value of Cp and Cv in degrees of freedom and Cp and Cv, okay. This is the relation: Cp is equal to F by 2 plus 1 into R, Cv equal to F by 2 into R, okay. And calorimetric principle to find equilibrium temperature, okay. And if the substances are mixed, we need to find calorimetric we need to use calorimetric principle to find equilibrium temperature of that mixer, okay. This is the equilibrium temperature: M1 C1 T1 plus M2 C2 T2 divided by M1 C1 M2 C2, okay. Case 2, when we have two different samples of the same material. Same material means specific heat or C will be same, so C will get cancelled from the previous equation and we get equilibrium temperature like in this equation, okay. N1 T1 plus N2 T2 divided by N1 plus N2. In case 3, if the number of moles will be same, then equilibrium temperature will be this. And mixture of ideal gas, in the case of mixture of ideal gas, final temperature will be F1 N1 T1 plus F2 N2 T2 divided by F1 N1 plus F2 N2. F here is the degrees of freedom of those gases, okay. And heat transfer is the Q by T, okay. Heat transfer per unit time, okay. This will be directly proportional to area. The heat transfer is directly proportional to area of cross section of that material, and inversely proportional to the thickness of that material, okay. Thickness of this material inversely proportional to that, okay. And directly proportional to the temperature difference between the both the places, okay, of that substance, okay. This is the relation. remember and use in solving problems. Okay, and the laws of thermodynamics and related parameters. So which law is related to which parameters in thermodynamics? Let us see. The Zeroth law. Zeroth law is the law of the flow of temperature, right? If A and B is in equilibrium, if A is in equilibrium, thermal equilibrium with C, and B is in thermal equilibrium with C, then A and B also in thermal equilibrium with each other, right? It is the Zeroth law of thermodynamics. And first law is all about internal energy, how internal energy is increased when we added heat. Okay, dq is equal to du plus dw, okay, internal energy plus work done on that system. Okay, and second law is the change of entropy. And entropy, when we added heat or energy, then entropy of the system increases, and we can calculate it from this formula, delta is equal to dq by t. This is the diagram of a heat engine. Okay, and third law is about absolute value of entropy. At absolute zero, for some substances entropy are almost equal to zero. That is third law. And isothermal process and adiabatic and isochoric and isobaric, these all are processes. Let's discuss them in short. Okay, in isothermal process, temperature is constant, right? So dq is equal to dw. So internal energy is 0, so dq, the energy and heat is given to the system, will be used to do the work. So work done is equal to nRT ln Vb by Va, and change in entropy is equal to nR ln Vf by Vi. Okay, these are very important relations, come frequently in exams. Okay, and adiabatic process. In adiabatic process, and there is no exchange of heat. Okay, then q is equal to 0, so dw is equal to du, internal energy, or then entropy, change in entropy is 0 as heat is 0. So given heat is 0, so entropy is 0. Okay, so in this case, adiabatic process, Pv to the power gamma is equal to constant, or we can also write Pv to the power gamma minus 1 is equal to constant. We can also write P to the power 1 minus gamma, look at here, 1 minus gamma into T to the power gamma is equal to constant. And work done in this case is equal to W is equal to 1 by 1 minus gamma into P2 V2 minus P1 V1. Okay, and isochoric process. In isochoric process, volume is constant, so work done is 0, right? Look at here, work done is 0, so du is equal to dq. Energy, how the amount of heat given to the system will be used to increase its internal energy in this case. Okay, and change in entropy is equal to ncv ln Tf by Ti, or we can also write ncv ln Pf by Vi. These are the graphs of these different processes. Okay, let's come to isobaric process. In isobaric process, pressure is constant, right? So we can see that the work done is P delta V. So change in internal energy is equal to dq minus P dV, and change in entropy is equal to ncp ln Vf by Vi, right? And also write, we can also write ncp ln Tf by Ti. Okay, right? And this is the graph of isobaric process. And I have said earlier that in thermodynamics there are thermodynamic potentials like internal energy, right, and Gibbs functions, Gibbs potential, right? And internal energy is what? From first law of thermodynamics we can see that du is equal to dq minus dw, and we also write du is equal to tds from entropy relation minus dw, also write tds minus pdv. Okay, For hydrostatic process, dW is equal to pdV. Okay, and all thermodynamic potentials will be exact differentials and perfect and exact differentials. What do you mean by perfect and exact differentials? Perfect differentials or exact differentials satisfy this relation. Okay, and Helmholtz free energy, this is also a thermodynamic potential. It is available energy for work in reversible isothermal process. The energy available in reversible isothermal process is the Helmholtz free energy. This is the relation of Helmholtz free energy U minus Ts. From calculating from first law and other relations, we can define change in Helmholtz free energy is equal to minus pdV minus sdt. Okay, this is very important relation. And enthalpy is also an thermodynamic potential, which is when a substance changes. Look at here, when a substance changes at constant pressure, enthalpy tells how much heat and work was added or removed from the system. Okay, at constant pressure and enthalpy will tell you how much work and energy is given or removed from that system. Okay, and enthalpy is mathematically we can define like this: S equal to U plus PV, and using the first law and other relations we can calculate or we can define this relation. Change in enthalpy is equal to TdS plus VdP, and this is the Maxwell equation. Okay, at equilibrium, also remember, in equilibrium change in enthalpy is 0. Okay, since there is no exchange of heat in equilibrium. Okay, and next the thermodynamic potential is Gibbs free energy, G. So Gibbs free energy is that energy that is available to do useful work from a closed system. In closed system, energy available to do work is the Gibbs free energy. Mathematically, Gibbs free energy is H minus Ts, and we can write like this: U plus PV, also F plus PV. Okay, change in G from this and this from first law we can define change in Gibbs free energy is equal to VdP minus sdt, and this is the Maxwell equation we can define from these relations. Okay, and work done for closed system, TdS greater than dq, right? TdS greater than dq, so change in Gibbs free energy is less than 0. And one important and very interesting diagrammatic approach to write Maxwell's equations is going to be very interesting and very fun to learn here, right? Let's make this diagram. Okay, this is a square. First of all, you create a square and then write P as Vt. Okay, then N, this is Z, then you just mirror image that you can remember or write Maxwell's equations very easily by drawing this diagram. Okay, I am going to explain to you. So this is P as Vt, right? First go in this direction, TP Vs. So write TP Vs and divide this and put an equal sign. Then what will be the constants? What there is T and second is P, so as P will be the constants. Okay, first will come S, then comes P, enclose them in bracket. S will be constant and P will be constant. Okay, this is the first Maxwell equation. In second Maxwell equation, you put this from here. Okay, P S T V, right? P S T V, P S T V, then divide them and put equal sign, and what will be the constants here? So first come Ps, so what will be next? Vt, right? V and T. Okay, the clockwise direction, like Tp SV, and like that Tp Ps, so it will be negative sign. Okay, in the clockwise direction it will be negative, and anti-clockwise direction it will be positive. Okay, this is very important and interesting to write Maxwell's equations. And this is the first Maxwell equation. Okay, this is the second Maxwell equation, third and fourth. These are the relations of TDS equations. There are three types of TDS equations. You can remember and ask very frequently in IIT exams and other JS and TFR exams. Okay, and chemical potential. Chemical potential is the heat added or removed from the system in the chemical or during the particle exchange. During the particle exchange, heat added or removed from the system is the chemical potential of the system. Okay, this is the relation of chemical potential. Mu is equal to ddn of G. Okay, differentiate useful energy with respect to n. Okay, these are also some very important equations in thermodynamics. Cp minus Cv is equal to T into dP by dt into at constant V into dP by dt at constant V. Okay, and Cp is equal to T dP by dt in constant V into dP by dt at constant S. Okay, this is very important and interesting to remember, and write, and don't forget to write and practice this Maxwell's equations from this diagrammatic approach. And this is going to be very beneficial and very interesting for all of you guys. And thank you for thank you for watching and enjoying this episode, and looking forward to see all of you again in the next videos. And thank you guys. And